All right. So these next two sections in Chapter 5, or really the last two sections in Chapter 5, deal with a lot of graphing. A lot of graphing. Today we're talking about symmetry in our graphs. And then on 2.5, we're going to talk about translations of our graphs, which means we're moving our graphs around in the plane. When we talk about symmetry, there's really three different types of symmetry that we're going to talk about. There's actually more, because you could be symmetric to really anything. You could specify a line or something like that, and you can be symmetric to it. But in terms of this class, what we're going to talk about is being symmetric to the x-axis, being symmetric to the y-axis, and being symmetric to the origin. So if you are symmetric to the x-axis, that's like our first picture. And that's where, if you folded your graph from top to bottom, your graph would lay exactly on top of itself. And really, the only thing that's changing is that your y's are becoming negative. Or if you fold it up, your negative y's become positive. You're negating your y's. So what do we do if we are trying to determine if it is symmetric to the x-axis? We're going to replace y with negative y and see what we get. If we replace y with negative y, we should get out the exact same equation at the end as we start with. That tells you that you're symmetric to the x-axis. If we plug in negative y for y into an equation and we don't get the exact same starting equation out, then we're not symmetric to the x-axis. And we're going to do examples of each of these, so you'll see more what I mean on that. These are kind of the general reference pictures. So you can be symmetric to the x-axis, and that's where your y's change. You can be symmetric to your y-axis, and that's where your x's change. That's where you fold your graph from left to right so that it lays right on top of itself. And that's where you negate your x's. So if your x's are negative, they become positive. If your x's are positive, they become negative. And the way that we would test the symmetry of a function or an equation is we would plug in negative x for x and see if we're getting out the same equation. And then the last one is being symmetric to the origin. That's where you're going to negate both your x's and your y's. So you would do both of those things. You would replace the x with negative x, you would replace the y with negative y, and see if we get out the exact same equation at the end. This is where you would fold your paper diagonally, and it would lay on top of itself, theoretically. I've been told my picture is not that great, but just go with it. I'm going to start grading your graphs a little bit harder. I'm going to be expecting those nice crisp circles. I won't. I'm not mean.
Yeah, you are.
No, I'm not. I'm not mean. I'm very nice. All right, we ready to try some of these? Maybe?
Yes.
Okay. What about you, Kelsey? You ready? Go faster.
Okay, I'm ready. I can read it.
Okay. Remember, you have access to my notes.
Yeah.
Okay. So we're going to test the symmetry for an equation. Find the symmetry for y equals x squared plus 6. And we're going to have to test it 3 different times because we need to test if it's symmetric to the x-axis, to the y-axis, or to the origin. So if we are testing if it's symmetric to the x-axis, that's where we replace y with negative y. And then we're going to work through it and see if we get the same equation. So instead of y equals x squared plus 6, I'm now going to have negative y equals x squared plus 6. I need it to be y equals, so I'm going to multiply everything by a negative 1. That'll get rid of the negative. Now I have y equals negative x squared minus 6. Does that look like our original equation? Nope. It does not equal this one. And since they're not equal, it's not symmetric to the x-axis. Symmetric. These are usually multiple choice, where it will be, I guess you can select all, because they'll have four options where it's symmetric to the x, symmetric to the y, symmetric to the origin, or not symmetric at all. There's usually the four options, and you're allowed to pick more than one of them. So if we are testing symmetry to the y-axis, that's where we're going to replace x with negative x, and we're going to do the exact same process. So we have y equals negative x squared plus 6. Notice what I did there. Just notice what we've talked about. There's a big difference between negative x squared and negative x squared. Remember? So we put it in the parentheses because anything that's x is going to get squared. And when we square that, we get x squared plus 6. Is that the same as the starting equation? Yes. So we are symmetric to the y-axis. And the last one we have to test is the origin. That's where we replace both. Replace x with negative x and y with negative y. And don't worry, I have some notes. Because you're like, this looks weird. Are we symmetric to the origin? No. So, if you are testing symmetry to the x-axis, you replace your y's. If you're testing symmetry to your y-axis, you replace your x's. If you're testing symmetry to the origin, you replace both. And here's a special note. If you are symmetric to both the x and the y-axis, then you are automatically symmetric to the origin. Notice we weren't symmetric to the x-axis, but we were symmetric to the y-axis, and then we weren't symmetric to the origin. That's because we need to be both. But being symmetric to the origin does not guarantee that you are symmetric to both the x and the y-axes. So this goes one direction. If you are symmetric to the x and y axis, automatically you are symmetric to the origin. But if you are symmetric to the origin, you are not guaranteed that you are symmetric to the y axis and the x axis. And I have examples. Not ones you have to work, just ones you can look at. In the examples, the circle is symmetric to the x and y axes, and it's symmetric to the origin. But the second graph is our graph of x to the third power. That's symmetric to the origin, but it is not symmetric to the x and y axes. If I fold that graph down, it's not going to lay on top of itself, or if I fold it from left to right, it doesn't lay on top of itself. So that's why you can go one direction with this, but not the other. You can kind of see the next example, and I want you to do it on your own and tell me what it is. Whoops, so sorry if I've moved up. Is that up too far for anybody? Like that first line? Okay, nobody's saying anything, so I'm assuming you're okay. If you're done taking the notes portion, feel free to work the example where you're testing the symmetry of x squared plus y to the fourth equals 5. You need to test the symmetry for the x-axis, the y-axis, and the origin. did you guys find?
They're symmetrical to all.
Yep, symmetrical to all of them. If you plug in negative y to test for symmetry to the x-axis, well, you're raising that to the 4th power, which means you're still going to get out a positive y, which means you have the exact same equation that you started with. So it is symmetric to the x. It's the exact same thing for plugging in negative x. You're going to square the negative, which means you're going to get out a positive answer. So the starting and ending equations are exactly the same. And then theoretically, you wouldn't have even had to test the origin, because if it's symmetric to the x and symmetric to the y, automatically it is symmetric to the origin. But I did do the work. Is there any questions about how we test symmetry in our functions? Okay. Symmetry is nice, but we talk more about it in terms of being even, odd, or neither functions. If you are an even function, then you are symmetric to the y-axis. That means that you can substitute negative x into that function and it doesn't change that function. That's what the f of x equals f of negative x means. It means we plug in negative x and we still get the same thing out that we get for positive x. Odd functions, though, are symmetric to the to the x-axis, and that's where we would switch out our y's. But in this case, they're talking about it in terms of the x's. So f of negative x is going to equal negative f of x. You are neither if you're not symmetric to the y-axis or the x-axis. So when we are figuring out if a function is even, odd, or neither, really what we're going to do is we're going to test to see if it's even. If it is, great, we're done. If it's not, then we move on and we say, okay, well, is it odd? And if it's not, okay, then we move on. And if it is, then we're done. So you kind of go down the steps of figuring out which one is even, odd, or neither. You should only have to test any function twice to know. Because if you're even, then you can't be odd or neither. If you're not even, then move on to odd. If you're odd, you're odd. And if you're not, then you move on, and the only option left is neither. And we're going to do 2 different examples where we're figuring out if our functions are even, odd, or neither. I say 2, maybe there's 3. There's 2. You ready to try them? Okay. Is f of x equals 5x to the 7th minus 6x to the 3rd minus 2x even, odd, or neither? So if it is even, then f of x has to equal f of negative x. So we have to figure out what f of negative x is. F of negative x is just where we put in a negative x anywhere that there is an x. Okay? So 5 times negative x to the 7th minus 6 times negative x to the 3rd minus 2 times negative x. Well, if you have 7 negatives, you have an odd number of negatives, so that's going to keep it negative. Same thing with x to the 3rd, because 2 negatives gives you a positive, but then you multiply it by a negative, you get another negative. So negative times negative will give you a positive 6. Same thing down here, negative times negative gives you a positive. If you have an odd number of negatives, it's negative. If you have an even number of negatives, it's even, or positive. Excuse me. So the question is this function the same as the starting function? No. So that means it's not even. F of x does not equal f of negative x. So not even. So then we test odd. That's where we have f of negative x equals negative f of x. Well, the nice thing is you just found what f of negative x is. That's what you just found. That's what this ending was. So f of negative x equals negative 5x to the 7th plus 6x to the 3rd plus 2x. That's f of negative x. Now, the question is what is negative f of x? Well, that's where we take a negative times the entire function that we started with. And if we take a negative times everything that we started with, do we get the same function that we just ended up with here? Well, I have, basically you're changing the signs of your original function. I had a positive 5, so now I have a negative 5. I had a negative 6, so now I have a positive 6. Negative 2, so now I have a positive 2. Are these the same? Yeah. So f of negative x does equal negative f of x, so it's odd. If we would have said no, if we would have found that this was not odd, then we would have proven it wasn't even and it wasn't odd, so the only option left is neither. That's why the most testing you're going to do is twice. After that, you're not going to find anything. If you do find that it's even, you're done. You don't have to test to see if it's odd. It's only if this is no do you have to test if it's odd. And if this is no, there's no more test for neither. It's just a given. Questions on this one? We're going to do one more, like this. Okay. Let's see if h of x equals 5x to the 6 minus 3x squared minus 7 is even, odd, or neither. So we start by testing if it's even. Even means f of x equals f of negative x. So I'm going to plug in negative x. Or, sorry, I guess these are h's, not f's. So h of negative x equals 5 times negative x to 6 minus 3 negative x squared minus 7. If you have an even number of negatives, you have a positive. So what did we find out? It is even. So while figuring out if something is even, odd, or neither is not super difficult, it does take time, and if you lose a negative anywhere, it gets all messy, and obviously you're not going to get the right answer. So this process is okay, but I show you that process first so you appreciate the quick method. Yep. Just look at the powers. So if all the powers in a given function are even, then you have an even function. If all the powers are odd, then you have an odd function. And if you have a mix of even and odd powers, you have a neither function. There's no algebra necessary, which is awesome. The one thing you do have to note, which is why there is a note up there, is that numbers, like constants, are considered x to the 0th power, which is classified as even. Remember, anything to the 0th power is 1. So if you have just a constant, like on that last example, you can see right up here we had a constant. So we have x to the 6th, which is even, x squared, which is even, and then we treat our constants like x to the 0th power. And while 0 is neither even nor odd, for this classification we do consider it to be even. And so thus we have all even. That's why h of x was even. The first one that we did, we had all odd powers. X to the 7th is odd, 3 is odd, and then there's no power written here, and when there's no power written here, we understand that to be a 1, and 1 is an odd number. So that is an odd function. So if you had, which I don't know if I do another example on here, but I'm going to do one right here. If I had g of x equals 2x squared plus x, yeah, it's a neither, because we have an x squared, which is even, and we have an x, which is odd. So we would have a neither function. And we don't have to test anything. No more negative x's getting thrown in there. You just look at the powers and determine if it's even, odd, or neither, which is pretty sweet. But you don't always appreciate the quick methods until after you've had to suffer through the longer methods. And so that's why we plug in that negative x. And it's nice to see how it works in terms of symmetry. But when it comes down to it, we can get the same information from just looking at the powers. Okay, yeah, that's what I thought.